Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on regression. It's part of a course called Analytic Methods for Lawyers. One of the most powerful tools for analyzing data is regression. Basically, it's a way of predicting values that are continuous or that are so close to continuous that we don't really care. There are an enormous number of types of regression: linear regression, logistic regression, Poisson regression, LASSO regression, ridge regression, Bayesian regression, and the list goes on. What I want to do here, though, is to focus on some of the ideas of two of the basic forms of regression, which are linear regression and logistic regression. And my hope is to make sure you understand the concepts behind doing a regression. We'll see regression again in our discussion of machine learning, and we'll actually see a little bit of that here as well. A note. I've produced some videos earlier on optimization and maximum likelihood estimation. If you haven't seen those before, you may struggle with some of this, and so I would suggest that you try those first to make sure that you've got the foundations that are going to help you understand regression better. All right, I want to first start by doing regression by hand, as it were. Not really by hand, I'm not going to be handwriting anything, but we're not going to be using some of the fancier Wolfram Language functions that let you automate this process fully. Rather, I'd like you to see and understand what's going on behind the scenes. So the first thing I'm going to do is to grab some old data on the price of homes in Boston, and they looked at all sorts of things. You know, how close is the house to the freeway? What's the crime rate? What's the pollution in the area? I think they looked at whether it was on the Charles River or not. Anyway, the exact nature of that data doesn't concern us. It's just a nice, fairly clean data set. And here what I'm going to focus on at the beginning are crime statistics and home price. So we're going to load that up, and you'll see what the data looks like. And I'm just taking 10 data points just to keep everything simple. All right, so there's our data. Here's crime on the x-axis, price on the y-axis. Now, what I want you to assume, and in some sense this is where a lot of the dirty laundry is hidden, that you can plausibly model the relationship between crime and price as a linear function, ax plus b, where x is the crime rate, and the only reason it's not exactly equal to ax plus b is a constant, is that there's some error that magically accounts for any deviation, and the only thing we need to specify is that the distribution of the error around the linear model is some normal distribution, and it's the same distribution regardless of the value of x. So we have what's sometimes called homoscedastic noise. Okay? So let's compute the for any given function ax plus b and some standard deviation of that normal distribution, which is generating the noise. For every data point, xy, let's evaluate the PDF of that symbolic distribution. We don't know the actual parameters. That's what we're trying to figure out. Let's evaluate the PDF of that normal distribution, symbolic normal distribution, evaluated at y. Now, let's do the following. Let's take our crime data. Let's apply this function, linear model normal error, to each element of that data. Let's take all of those results and total them up, and then let's just take the negative of that total. So we're going to take our crime data and run it through this operator pipeline. Okay? I'm actually going to do, well, let's do that. First of all, let's evaluate this function so it's in the kernel. See how it's color-coded blue, and that's a hint to me that the kernel doesn't know what I'm talking about? All right, we're going to compute this. We'll call this negative log likelihoods. And there we go. It's some very elaborate expression involving logs and pi and sigma and a and b. I want to show you a little trick that can make this easier. I'm going to add two operators to our pipeline. The first is called power expand, which just expands out any powers, any products, and then I'm going to simplify the result. So let's do it again. And you'll see how I think that is a much simpler expression for the negative log likelihood of a model that has A, B, and sigma as its parameters. So, in fact, if I hold sigma constant, if I just pick some value for sigma, then this now only has two variables in it, A and B, and I can plot them. So let's actually plot the negative log likelihood as a function of the two parameters A and B, and I'll just plug in 5 for sigma, and I'll let A run as shown and B run as shown, and there's some iconized code that there's no need to trouble you with. All right, so we plot that out, and we can see that we kind of have a little valley here, and there's that happy spot at the bottom of the valley, which is the values of A and B that is going to minimize the negative log likelihood, which, after all, is what our goal is. And so we can do this in a couple of ways, as I believe I showed you in the videos on maximum likelihood estimation and numeric and symbolic optimization. One is a calculus-based method where we take the gradient of the negative log likelihood expression with respect to A, B, and sigma. We set those gradients equal to 0, and we try to find the solution to when they are equal to 0, adding one little factoid, which is that the standard deviation sigma has to be positive. There's no such thing, at least in my world, of a negative standard deviation. It's going to produce an annoying warning message, not an error message, a warning message, which I don't need for you to see, so I'm going to tell it to be quiet. And then I think I've mentioned before that solve can sometimes produce multiple solutions. Here there's only one, so I don't need to clutter your brain with more solutions. So let's run that. It's going to do the calculus, the algebra, and there we go. And you can see that it has found the bottom of the valley. A equals negative 14, B equals about 25, and sigma happened to be 5.66, so my little guess wasn't that far off. All right, so we don't need that. If I just tell Wolfram Language that, hey, sigma has to be greater than 0, I can sort of have it do the calculus automatically without having to go to this formation of gradients and threading and solving by just running argmin on that. And there we go. You get the same results, just in a slightly different form. And we could do this all in one step, actually. Look at this. We just take our data. We apply our linear model normal error, which computes the log of the PDF of the y, given a symbolic normal distribution. Total it up, negative it, make it easier to deal with algebraically by power expanding and simplifying, and then taking the argmin of it to find the minimum values of A, B, and sigma. And so let's see how long this all takes. Done. Okay. So what we can then do is to show, hey, this is an equation, right? We have A and B, so we now know what AX plus B is. So we'll take AX plus B, we will plug in with the replace all operator /dot, the solution that we stuck in calculus MLE. We'll let X run from 0 to 0.7 because that's the range of the original data. I'll make a nice dashed red line to show the best fit, and I'll combine our original point plot with our new line. And voila, there is the best fit line for that data. This is the maximum likelihood estimator for a linear model for this data. Again, for better or worse, I'd like to minimize the amount of black boxiness in discussing statistics, because if you don't understand the concepts, then it's easy for you to be fooled by people who have their own ideas about what results they want. So let's talk about what's really going on in a linear regression. Basically, what the software is going to do, if it's any good, is to develop a probability distribution of what the regression coefficients, A and B here, would look like if the null hypothesis were true. That is, they're going to try and figure out what would we expect to see in A and B if if X had no relationship with the output Y and the intercept term were 0. So let's call that distribution script capital T M3. The script capital T is because it's sort of related to something called a T distribution, the M because it's a multivariate distribution, and the 3 for so it doesn't get confused with 1 and 2. So it's a multivariate distribution because it's going to pop out values for A and B. Okay? That's its job. It just produces values of A and B according to its internal operating methods. All right, because it's a multivariate distribution, we can develop marginal distributions of script capital T M3, and let's call those distributions T M1 and T M2, or T M sub I, where I, in this instance, is 1 to 2. And that'll give us null distributions of each coefficient, here, A and B. So here's what we could do. We could look at our own values of A and B, and since each Ti is symmetric, and there you are going to have to trust me, compute a two-sided p-value for the A coefficient and a two-sided p-value for the B coefficient. In Wolfram Language, as I've discussed before, we could use rarer probability to do this, or you could basically add the survival function of each Ti evaluated at the statistic A or B to the CDF evaluated at its opposite and add those up. That's why I like rarer probability. It's much simpler. And this process would tell us how likely it is that we would see coefficients as extreme as the ones we have if the null hypothesis were true, if X had really nothing to do with the value Y, and if the intercept term were likewise 0, and that all we were seeing was noise. We could do that, and maybe life would be simpler in the modern era. But here's the problem. To do this, we kind of need a fancy computer. We need to be able to compute a rarer probability, PDFs, survival functions, CDFs, for each of those T, M, I. And that means that since TMI can have it has two parameters that are going to be changing depending on what the regression looks like, we're going to need a lot of tables, okay? Because we're going to be working from printed out tables, like I did when I was a student in college. So it sure would be nice if we could figure out a way so that we only needed one table or fewer tables. So what if we transformed the marginals? It turns out that there's a simple transform that does the job. We divide the output from each marginal of TM3 by that marginal's standard error, which it turns out is the second parameter of the marginal distribution. When you do that, you get another distribution, T sub I, not Tm sub I, that can be defined with just one parameter, not 3, just 1. And so you need a lot fewer tables. You just need a table for when that parameter is 1, and when it's 2, and when it's 3, and when it's 20. And if you have a 17, you might use some interpolation, and sort of take an average of, well, what would it be if T were 15, and what would it be if T were 20? All right, so that tradition of transforming the marginals of the joint probability distribution of the regression coefficients continues to be used even though it's not strictly necessary anymore. There's still some remaining utility to it anyway. You take your regression coefficient, you divide it by the standard error of the marginals of the joint distribution of the regression coefficients, and you get something that's related to the regression coefficient but not quite the same, called a t-statistic. That's what this t-statistic thing is. And you then compute a two-sided p-value for your t-statistic by looking at the rarer probability of this distribution t sub I, that transformed distribution. And that is how you determine in a regression if your results are statistically significant. That is, should you have any reasonable doubt that your null hypothesis, which is that the variable is irrelevant, is true. Just so you feel even more confident, let me illustrate this. This comes from our data, okay? Here is, in fact, the TM3. This is the joint distribution of the regression coefficients. Now, the one black boxiness you have to indulge is don't ask me how I figured this out. Let's take our first marginal. We get a student t distribution. We've moved from a multivariate distribution to a regular t distribution. Now, let's transform that marginal distribution by dividing it by the second parameter. Here, that 2.7987, which is the standard error associated with that variable. We get a new distribution, student t distribution with a first parameter of 0, a second parameter of 1, that's the effect of the division, and the third parameter remains 8. But it turns out that where you have 0 and 1 as your first two parameters, you don't really need them, and you can describe the distribution as a simple student t distribution. But really, where you have a t distribution and the first parameters are 0 and 1, you can just skip them. And you basically have the t distribution with a degree of freedom, that third parameter, of 8. And to prove that, let's just take the PDFs of a 3-parameter t distribution where the first two are 0 and 1, and just a single parameter t distribution where the lone parameter is 8, and we'll see if those two are equal to each other, and it turns out that they are. So, perhaps more than you ever wanted to know, but that is what is going on with regression. And remember that number 2.7987? I say we're going to see it again. I just showed you how to do a regression using maximum likelihood estimates. Sometimes that is computationally challenging. There's another method which is called using penalty functions. The idea is that you compare each predicted result to the actual value. You compare the result your model gives you with the actual value, and to the extent that there's a difference, you penalize it. And the idea is to come up with a model that minimizes, in this case, the sum of those penalty functions. Ideally, we're going to choose a penalty that ends up giving us the same result as the MLE. But there's no actual requirement that that be so, and in fact, sometimes you want to choose a penalty function that leads to a different result than the MLE. So what I'm going to do first is, here's my penalty function. We're going to take what our model predicts, ax plus b, and subtract from that the real value of y. We will apply that to our crime, and then we'll take the absolute value, of that difference. That's important. We'll take the absolute value of the difference between our prediction, ax plus b, and actuality, y. We'll apply that to all our data. We'll total up all our penalties. We will then, we don't need, actually this is sort of, we don't need to negative it here. In fact, I didn't. Why don't we just take that out? And then what we're going to do is we will minimize the sum of the penalties and find the values of a and b that minimize the sum of the penalties. And that'll be our, quote, best fit, close quote. So we can do that. We get this, and we can then use those coefficients, which if you remember is a little different than what we got when we used MLE, and we can plot in a dotted purple line the best fit using this method of absolute deviations. Okay? It's not terrible, but Maybe there are some things that are better. Here's another penalty. Here what we're going to do is we're going to take those absolute values of the differences between our prediction and actuality. We'll go through the same thing as we did, but now we're going to have an additional penalty, a bonus penalty, that depends on the size of A and B. The bigger A and B are, the less we like the result. So we're sort of balancing making A and B small against making these absolute deviations small as well. So we can do that, and we again get somewhat different results. We can do the same plot. This time I'll make it orange. And we get another fit. Here's another penalty. This time what we'll do is we'll take our prediction, we'll subtract off the actual value, and instead of taking the absolute value, we'll square the difference. Then we'll take the sum of the squares. So we're going to take the sum of the squared differences between the prediction and actuality. If you want to call this a residual, because it's sort of what's left between the model and the actuality, we're taking the sum of the squared residuals. And we will then find the values of A and B that minimize the sum of the squared residuals. And we'll call this the OLS penalty, where OLS might just happen to stand for ordinary least squares, least. And we get more values for A and B. We'll do our same thing. This time we'll plot our best fit in green. There it is. By the way, if you want to see some interactive demonstrations that look at some of these penalties, you can do so here. There's more. In fact, there are an infinite number of penalties, aren't there? It's the same thing that we did before, the sum of the squared residuals, but we're going to add in this additional penalty where if A and B are small, this penalty is minimal. But if A and B get big, since we're squaring them, this can get quite big. And we'll call this, just for the heck of it, a ridge penalty. And we get yet another answer. Again, same thing. I'll plot our best fit using this ridge penalty in a brown dotted setup. So there you go. We've done a lot of penalties, lots more we could do. And now let's take all of our best fits and we're going to combine that with our data, and then we'll stuff a legend on it. So here's our code, and let's execute it. And you can see the various best fits that we've produced. Now, if you look at this very carefully, and let me magnify things here greatly, do you see that the red line and the green line seem to fall right on top of each other? So, what are those red lines and green lines again? The red line was our maximum likelihood estimate. Our green line was our ordinary least squares estimate. And so this is suggesting, it's not a proof, but it's a suggestion that ordinary least squares might be a computational shortcut, at least in some cases, to computing a maximum likelihood estimate. And in fact, it is a computational shortcut. And one of the things we sometimes want to do is in different contexts where we have different kinds of models that we're looking at, maybe not linear regression, maybe we're looking at logistic regression or Poisson regression or X regression. We might want to see if we could find a penalty function which would lead us to the same result, because if we do so, that can often be computationally advantageous. Let's discuss a little more complicated form of regression. Up until now, I've assumed our model was linear and that we had one basis function of x. That is, our model was, here we have x, and here's what we're going to do with it. We're going to multiply that x by some value a, and we'll add b to it. So the only way x got involved was through multiplication by a. But that's not necessarily, we don't have to restrict ourselves in that fashion. What if I assumed x could appear in two places? We could have y is equal to ax squared plus bx plus c plus some normally distributed noise that didn't depend on x. I wonder what the best values of a, b, and c would be to fit our curve to the data. So it's the same idea here for maximum likelihood estimate. We're going to form a symbolic normal distribution where the mean of the normal distribution is a function of x, a quadratic function of x, still have an unknown standard deviation. We're going to compute the PDF of that normal distribution evaluated at y, and then we'll take the log of the PDF of the symbolic normal distribution evaluated at y. And that function that takes x and y and produces that number, I will call the linear quadratic model normal error. All right, there we go. And now, let's do what we did before, which is form the negative log likelihood. So we're going to take our crime price data, we're going to apply that linear quadratic model normal error function to each element of the data. We're going to add up those likelihoods. We're going to take we're going to add up those log likelihoods. We're going to take the negative of it. We'll do a little bit of algebraic simplification by power expanding and simplifying. And lo, we have an expression, and it's got a lot of stuff in it, but it's not too brutal, and it just has A's and B's and sigmas and a bunch of numbers, and C's and a bunch of numbers. So we could do the same thing that we did before. We could use the calculus method, where we're going to take the gradient of that expression, negative log likelihoods quadratic, with respect now to a, b, c, and sigma, the things we're trying to figure out, set them equal to 0, determine the conditions under which those are equal to 0, provided that sigma, the standard deviation, is greater than 0, shut up an accursed warning message, and then just take the first solution. So there we go. We get some values, and we can plot the resulting curve. Here's our original data, which we're going to combine through show with a plot of a symbolic parabola, but we're going to plug in the specific values we have for A, B, and C. We'll run that over the range of our data that we have, and we'll make it dashed and red, because I like dashed red. And there we go. That is the MLE estimate of a quadratic fit to our data. I know what you're thinking. I wonder if we could just use argmin instead of going through all this calculus stuff. And let's see. Here's argmin. Here's what we're trying to minimize. Here's the constraint that the standard deviation has to be greater than 0. And here are the variables that will minimize the expression. So, yep, we can use argmin. We don't, in this instance, have to use calculus. Okay, so far, I've just looked at one piece of data in trying to predict home prices. I've used crime. But what if I have multiple variables? What if I want to use crime and maybe, what do I end up using here? Access to freeways, okay? So, can we do that? The answer is yes, and to the computer, really, the problem doesn't look any different than what I just did, where I used x in multiple ways by taking x squared and x, and here we're just taking x and y, as it were, crime and access. But to the computer, it's the same thing, and indeed, there's something called a design matrix, which is basically you look at the data on the assumption that for each basis function, you create a column reflecting the application of that basis function to the data. And in fact, you can run a regression simply from its design matrix. I'm not going to go further into that because I don't believe I used design matrices further in the course, but if you hear that term, and now you know what it is. All right, so let's get our same Boston Homes data that we had before, And instead of just getting the crime data, let's get the crime and access data. This code doesn't need to concern you. And we're just going to make a 3D plot of the way that crime, freeway access, except I don't think they're called freeways in Massachusetts, they're called highways or terrible roads, and the relation of those to the price of homes. All right, there is our plot. Let's do the same thing we've been doing. We take our model, which is A times X, where X here is crime, B times Y, where Y here is access. We add in an intercept term C. That forms the mean of our normal distribution. Some error standard deviation, sigma. We get a symbolic normal distribution. We apply that to our price data, which here is played by Z. And we take the log of this likelihood that we just computed. And so that's the first thing. Let's just tell the kernel, hey, now you know what multivariate model normal error is. And now we're going to do the same thing I've been doing. We're going to take that function, apply it to all our data, sum up those log likelihoods, take the negative of the sum of the log likelihoods, do some algebraic simplification by power expand and simplify, and there it is. We have an expression in A, B, C, and sigma. By this point, you're probably getting bored. We can take for many reasons, but we can take the gradient of the negative log likelihoods with respect to our parameters A, B, C, and sigma. We set those gradients equal to 0. We solve them on the condition that sigma has to be greater than 0. We shut up an annoying error message, and we take the first solution, and there we go. I'm going to leave it as an exercise for you to figure out if you could just use the argmin method. Hint, you can. And now what we can do is we can use parametric plot 3D. The x-coordinate is just the x value, the y-coordinate is just the y value, and x here is crime, y is access, and the z value, what we're trying to predict, is ax plus by plus c, plugging in for a, b, and c the values we got here, and we can make a nice three-dimensional plot showing a plane that fits to our data. And just for fun, we can rotate our plane and see how the data is doing. Your professor is very visual and likes to make interactive things that help him and hopefully others understand what's going on. So that's what this code is. You are not responsible for this code, but you are responsible for playing with the result where I'm trying to show you how does the, and it doesn't quite fit here, we're going to have to shrink ourselves a little bit. Okay, now it'll fit in the recording window. And so you can see how varying A, B, and C varies the sum of the squared residuals. So as I do this, my goal would be to find the values of A, B, and C, I'm doing much better now, that minimize the sum of the squared residuals. I'm getting... So anyway, it might be something like that, and I'll let you play around to see how choosing different values of A, B, and C form a different plane where you're going from the, basically from the green true value to the red predicted value, and you're forming basically the squares of each of those residuals and adding them up. Isn't there an easier way of doing all this? And the answer is yes. And again, you might question, well, then why did I show you the hard way? And I showed you the hard way because I want you to understand what's going on behind the scenes so that when you are confronted with other people's work, you can try and make sure that they're doing it properly and not cheating. If you don't understand what they're doing, they can fool the heck out of you. All right, let's open up this area. And here's the simple way to do it. Okay, we're going to use a function called linear model fit. The first argument is the data, and the data must be in the form basically of a matrix in which the last column is the thing you are trying to predict. You're then going to set forth your basis functions, which here is just crime. You could say it's 1 and crime, 1 basically representing an intercept term, but unless you tell Wolfram Language, hey, I really don't want you to use an intercept term, it's going to assume that that's the case. You then need to tell it what are the actual variables, and it may seem duplicative to do this, but trust me, there are instances in which these things can be different, in fact, as it is right below, so you do need to tell it what the variable is that you're trying to predict. So that's the structure of the linear model fit command, and there we go. We get an answer. That was a lot simpler, wasn't it, than doing all that MLE and penalty stuff. We can take a quadratic model. Now we have 2 basis functions. We have crime and crime squared. What we're trying to predict is still the same thing, crime, the coefficient in front of crime. And we get a fitted model. Now, remember I told you way back, I think when you see gray stuff, that can mean that you're dealing with a Wolfram Language object, and there's much, much more that you can learn about it. So linear model produces a fitted model object. And then what you can do is ask Wolfram, hey, what do you know about that fitted model object? So here I'm going to say, what properties do you know about crime model? Crime model is the result of performing linear model fit in this simple fashion. And so let's run that. And oh my goodness, it knows a lot. Okay? So it knows about the adjusted R squared and the ANOVA table sum of squares and the catcher matrix and the eigenstructure table indexes and the mean prediction bands and all sorts of stuff. Okay? You are not going to learn all these things. I actually don't know what a few of them mean. Like I really honestly don't know what the eigenstructure table eigenvalues are. But we are going to learn what some of them mean. We're going to learn the most important ones. So what's the best fit? That's an important property of our crime model object. And it tells us here's basically your equation to predict home prices. But these numbers, by the way, are in thousands. And so this was back in the day when you could buy a home in Boston for $25,000, which gives you an idea how old this data is. You might want your data, your function, to be in the form of a pure function rather than an expression here, so that function will do that. You might want to take this function and apply it to some value for crime. So there's the abstract thing. You can recover the expression that way. You could also say, well, what if crime is 0.02? And you could find out that that's going to be your best prediction for what the price of a home is, whereas if crime was 0.3, the price of the home under this model would go down. Or you might just want a list of the best fit parameters. This is very similar to what Argmin gave us. There they are. Okay. You can also find how far was each prediction from the actual value, and that's called a fit residual. We'll see a lot about residuals in this course. But for now, we're going to find out what the fit residuals are. A positive number means your prediction was too high, and a negative number means your prediction was too low. And you can see, by the way, this simple model is not doing a great job in predicting home prices. Evidently, there's more than crime to predicting home values. If you don't remember what basis functions you use to generate the data, you can generate the model, you can recover them. It was 1, the intercept term, and crime. If you want to find out 2 things at once, you don't have to write 2 separate commands. You just write the properties, wrap the properties in a list. And there we go. So that's sort of how to work with a fitted model. Now let's look at perhaps one of the most important properties of a fitted model that's generated by linear model fit. That's called the parameter table. Let's look at it. Okay. And let's in fact magnify this just so we can magnify its importance in your mind. All right. Let's look at this. This is telling us our best estimate of what the coefficient is It's basically 25.78 minus 14.37 crime. This is telling us the standard error around this estimate. And do you remember how I told you you might see that number 2.7987 again? And that was the second parameter to the multivariate t-distribution. I'm sorry, it was the second parameter to the first marginal distribution. Well, there it is. That's the standard error. If we divide the estimate by the standard error, we get the t-statistic. And then if we know the degrees of freedom with the associated t-distribution, we can compute the p-value. That is, what is the likelihood if the true association between crime and home prices was 0, we would get a result as extreme as negative 14.37. And it's saying, by chance, that could happen 15% of the time. Therefore, if we use a conventional cutoff of 0.05, we have not disproven the null hypothesis. Is the price of a Boston home 0? No, the p-value here is very, very small. Instead of getting the data presented this way, and let's go back now to the regular level of magnification, we could just get it as the entries and wrap it up in a grid. All right, so it's a very similar thing. I just went through with you what those entries mean. This is the Wolfram Language way of presenting the results of a regression. You know, every program, Stata and R and everything else, has its own little way of doing it, but most of them are very, very similar. And so I think if you understand this parameter table output, you will be able to understand the output from most decent software programs. So, right, let me talk about stars. Sometimes in the table, there will be a star at the end, or maybe 2 stars at the end of the p-value, and that will tell you how small it classifies p-values according to their smallness. And oftentimes, if it's 0.05 or less, you get 1 star, and if it's 0.01 or less, you get 2 stars. I am not a big fan of the star system because I think the cutoffs are arbitrary, and I think you should just be able to look at the p-value. That's a lot simpler. So far, we've looked at linear regression. I now want to look at another form of regression called logistic regression. Now, when we did linear regression, the y value could basically be anything. And that meant that we could use normally distributed error because the domain of a normal distribution is the entire real number line, so that we could explain our result in terms of ax plus b plus some normally distributed error. But sometimes we want a model that can only output a small set of numbers, not 37.2 or negative 58.3, but only numbers between 0 and 1, or maybe just 0 and 1 itself. So in this instance, a normally distributed error isn't very good. We might want a different kind of model. In fact, we might want a model that predicts the probability that some set of inputs will lead to a 1, and it can then choose among 0 and 1 to maximize the utility of that choice. And the most common statistical tool to do this, although not the only one, but I would say at this point the dominant statistical tool to do this, is logistic regression. With linear regression, our model was the PDF of a symbolic normal distribution, and that normal distribution had a mean that was equal to some linear function of the independent variables. By the way, independent variables are sometimes called covariates, and they're sometimes called features. By contrast with logistic regression, our model is the PDF of a Bernoulli distribution, not a normal distribution, a Bernoulli distribution, whose mean is a logistic function of the independent variables. So, what do I mean by a logistic function? Well, Here's the Wolfram Language command that gives us a logistic function. They call it logistic sigmoid, and I'm going to make it a function of ax plus b. So there's a little linearity inside of the logistic. And so that's the formula. That's what we mean by a logistic sigmoid. I can show you here in this manipulate what the effect of changing the a's and b's are. So right now, the a value, the thing in front of x, is negative, and the b is negative. And you can see that it looks like the, and I'm plotting, it looks like it's at 0.5, sort of halfway down, at about -1. As I move my b value, you can see that the curve is moving to the right. And as I change my a value, you're going to start to see it get shallower. And then, as I cross 0, it flips. Okay, and now it's going uphill. So when it's uphill, the higher the x value, the more likely it is, in some sense, that the y value gets closer to 1. Whereas if a is negative, then the higher the x value, the closer to 0 we get. So that's the property of a logistic sigmoid. Its values are bound between 0 and 1, which is a very good thing if you're trying to model probability. Just as I did with linear regression, where I kind of started from scratch, I want to start from scratch with logistic regression using a maximum likelihood estimator. So I'm going to take data from the Titanic data set. I think we've seen it before, but it basically talks about the fates of the passengers on the Titanic. For simplicity, I'll just take 50 of them, and I don't want to deal with missing data, so I'm just going to take the first 50 rows of the data set for which we have good data, and I'm going to scramble them because, as it turns out, the data in the Titanic is sorted, and that can lead to very misleading conclusions. So let's just do that. And here's our data. It's just, here's your age, 1 is you survived, and 0 is sadly you died. So one thing I can do is I can group the data according to its last element, which is whether you lived or died. And then I can make a number line plot showing the distribution of your ages. You're not responsible for this code, but there it is. Here's the distribution of people who died, and here's the distribution of people who survived. So what I can do is now I can calculate the negative log likelihood of seeing this data. So let's go through it. I'm going to take a logistic sigmoid, which is symbolic and has parameters a and b in it, and we're going to multiply the x value of our data by a and add b. Function expand, you don't really need that here, but I'm going to include it. We're going to then take the Bernoulli distribution of this logistic sigmoid. We're going to then take the PDF of the output of that Bernoulli distribution, and then we're going to take the log of it. We're going to apply this to all of our data. Here's our data. We're going to apply it to all of our data. As before, we're then going to take the total of these log likelihoods. We're interested in the negative log likelihood, so we multiply by -1, and we use power, expand, and simplify to make the algebra that we're going to do a little easier. And there we go. Okay, so we've got an icky expression in A and B, but that's it. We've just got a lot of A's and B's. Okay, maybe we could find the value of A and B that minimizes this negative log likelihood. So let's set it up. Take the gradient with respect to A and B, equal them to 0, and then I'm going to use find root. It turns out that it's very hard to do this, or maybe impossible to do this analytically, but you can use numerical methods, and I just give it some guesses. I'll say, oh, I think A is probably 0 and B is probably 1. So we do that, and it tells us actually you do best if A is -0.04 and B is 0.93. Or, as it happens, I don't need to use this calculus-based method. I can just use our friend argmin, and we get the same answers. So those are the parameters A and B that minimize this negative log likelihood. This is going to be our best fit, and we can now actually show that best fit. It's not a very good fit, right? Because all the data is up here. It's either at 1 or at 0, and here's our curve, but it's giving you the idea that the older you get, the less likely it is, sadly, that you are going to survive. Is there a simpler way? Yes, in Wolfram Language there is, and it looks very, very much like linear model fit. You just use something called logit model fit. You give it your data. Again, it's a matrix in which the last column is what you're trying to predict. Your basis functions. Here I did include the 1. I'm not sure why. And x is simply our crime as it happens. And here's the variable that we're trying to get information about, x. So we do this, and we get a fitted model object, okay? Just as we did before. That fitted model object has a lot of properties. You'll notice that many of the properties are the same as they were when we did linear model fit. I see basis functions, best fit, best parameters. But if you looked at that earlier stuff carefully, you'll see we see things that are new. Deviance residuals, deviances, parameters z statistics. So the properties of a fitted model can depend on what process generated it. We get information out of the fitted model object the same way as we did for linear model fit. We can get the function, the best function, there it is. We can apply the function to a symbol crime. Wait a second, we're not doing Boston housing anymore, we're doing the Titanic. So you could call it crime, but that wouldn't be very evocative. We should do age. All right, so here's the probability of dying as a function, of surviving as a function of age, and I could actually put a number in here and see that it really might not be good for your average 63-year-old, although if you were 24, it's looking somewhat better. All right, but let's go back and make that age. All right, and we can get the best fit parameters as we did before. Again, probably the most used property that we're going to get out of a fitted model that derives from a logit model fit is the parameter table. It is very similar in form to the parameter table that we got when we did linear model fit. We have our estimate of the parameter. We have our standard error of the distribution, although here the standard error is not coming from a multivariate t distribution. It is coming from a multivariate normal distribution. That's why it's called, when we divide the estimate by the standard error, it's called a z statistic. For some reason, normal distributions seem to go along with z. And we can compute a p-value. As we did before, what is the probability you would see a coefficient in front of this variable as extreme as the one we do if the null hypothesis were true? That is 0.0574. The null hypothesis being that there's no relationship between age and the probability of surviving on the Titanic. Okay, what on earth do these coefficients mean? And in fact, there's been a recent rebellion against using logistic regression, in part because the coefficients are difficult to interpret, and some people have been using linear models on things where the results are probabilities. I don't think that's a great idea, because a linear model could lead to a probability of 137% or negative 52%, which have no actual meaning. Nonetheless, it's thought the advantages of interpretability are so great that people are willing to live with that conceptual problem. I think the better way to go is to try and understand what these coefficients are. And you remember that in my Bayes' law video, I talked about the Grant-Sanderson method of understanding Bayes' law, that it was a way of updating, not probability, but updating a related concept, odds. Let's see this concept in action. Supposing I take my fitted model that I developed all the way up here, LOMF, and LOMF can work as a function, and I just apply LOMF to 43. So I now get the probability that a person age 43 is going to win. But instead of expressing that as a probability, we could express it as odds. And if you remember from that earlier video, odds are the probability divided by 1 minus the probability, and therefore can range anywhere from 0, when probability is 0, to infinity, when probability is 1. So we'll take that function right there and apply it to LAMF of 43 and get the odds of someone surviving if they are 43. So it was 0.45. And we could take it one step further and compute the log of the odds. So negative 0.79, because negative 0.79 is the log of 0.45. So just hold that number in the back of your head. And now let's compute the log odds of LAMF for someone who's 1 year older. Negative 0.83. And now let's calculate the difference in the log of the odds. How have we updated the log of the odds as a result of going from age 43 to age 44? And it's negative 0.0402245. And I say we've seen that number before. It is the coefficient in front of age. So, just as Bayes' laws can be thought of as a way in which a test updates odds, logistic regression can be thought of a way in which a regression model updates the log of the odds. So I find that a helpful way of interpreting logistic regression, and maybe it saves us from the perils of resorting to a linear model for data that really isn't suited to it. You remember we calculated the residuals for linear regression, the difference between the predicted value and the actual value. With logistic regression, we can do the same thing and more. So we have multiple kinds of residuals with logistic regression. The two I'm going to focus on here are the fit residuals and the deviance residuals. With the fit residual, a positive number means that the prediction was too high, and a negative number means that the prediction was too low. And so it's the same thing. That is, here are the fit residuals, and here I'm going to show that the fit residuals are the same as the real value less the predicted response. So those two are exactly the same. So you can have fit residuals with logistic regression. Usually, though, with logistic regression, you use something else called the deviance residual. And deviance residuals can seem completely mystifying, but they're a lot easier to understand if you've seen cross entropy before. And so let's start with something called deviance, which is double the cross entropy between the predicted distribution of survival, the source, and the actual distribution of survival, the target. That is, deviance is basically almost exactly the same thing as cross entropy. The only reason we double it, it's the same reason that we divided by the standard error. It's so that we have a distribution that's a member of the chi-square distribution family, and we only need one table, as it were, to try and understand the results. Here, what I'm going to do is to compute the deviance residuals by hand. I'm going to take the log, or I'm going to compute the cross entropy. It's basically, we're going to weight the logs of the prediction and 1 minus the prediction. Those are our two possible outcomes, the predicted value and 1 minus the predicted value, and weight those by the actual response, the truth of the matter, and 1 minus the truth of the matter. And then I'm going to double that, and that is the deviance. To confirm that, I'm going to use something called map thread, and we may have seen map thread before, but here's the idea of map thread. We have some function g, and we have values a and b, and c and d, none of which have been defined before, and right, we need to wrap those up in a list, which I forgot to do. Okay, and the idea is you take the first element from each of these lists, and then you stick a g in front of it. And you take the second element of each of these lists and you stick a G in front of it. And if we did this, you just do the same thing as before, and then you take the third element and the third element and you stick a G in front of it. So that's what map thread does. And here I'm just using deviance playing the role of G, the responses playing the role of the list of first arguments, and the predicted responses taking the role of the second argument. So that's what deviances are. The deviance residual is very closely related to it's a variant of the deviance. If the response is 1, if the truth is 1, it's the square root of the deviance. If the response is 0, it's the negative of the square root of the deviance. And if you sum up all those deviances over all the data points, you should have a chi-square distribution if the model is useless. And that lets you compute a p-value for how well your regression has done, because you have a distribution, chi-square, if the null hypothesis that the model is useless is true. You have a sum of deviances as a statistic, and you can now see how likely is it that you would get a result as large as the deviance that you do if the null hypothesis were true. That lets you compute a p-value for your measure of fit. Okay, something a little simpler, thankfully. Just as you can have linear regression with more than one basis function, you can have logistic regression with more than one basis function. So here, we're going to take our age variable, and we're going to try and do a logistic model on age squared and age cubed. There it is, so you can do that. And just as you can have multiple linear regression, you can have multiple logistic regression. Here I'm going to use age and gender to try and predict whether someone is going to survive on the Titanic. We get our little data that has age and gender. And now we're going to do a logistic model. Here are the two basis functions, age and gender. Here are the variables, age and gender. And I do want to tell the computer, hey, gender is a categorical or nominal variable. It doesn't take on numeric values. Just remember that. And by the way, I'll do that. I could also, of course, combine these two ideas and do age squared. And now we are combining multiple basis functions using age and gender. In fact, I could use age time. Well, actually, age times gender won't work because gender is nominal. But if a gender were numeric, I could do that. So you can do all those things, put all those things together. This concludes, you will be happy to know, the required viewing on regression. There is a little extra segment that I've put together on how to think about linear regression as being a form of neural network. If you're interested in neural networks, please feel free to watch. I'm going to guess it's going to take 8 or 9 minutes remaining time of this video. If not, though, you will be happy to know that you have learned everything I wanted you to know for now about regression. There's actually a lot more to learn, and we'll have a couple more videos on things like lasso and ridge regression, more on residuals in some of the future videos. In this optional part of the video, I want to discuss how to implement the idea of linear regression with a neural network. So I know we haven't studied neural networks yet, but you're going to get a very beginning idea of it here. So supposing we have two inputs, crime and highway access, as we did earlier in the video, and I want a network to output a single number, a scalar, that represents the predicted price. So it's going to be a very simple network. It's going to have just one layer, and a layer is sort of a word for a fancy function that moves us from an input of length 2, crime and highway access, to a scalar output, just a number, the likelihood of surviving. I'm sorry, we're out of Titanic land. We're back in Boston housing land. So we have got crime and access, and we're going to try and predict the housing price. Okay, so Here's how we're going to implement it. We're going to say that it's a chain. That is, there could be lots of functions that you keep iterating. You go from one to the next, to the next, to the next, kind of a pipeline. As it happens here, there's only one part in the pipeline. And I am going to tell it, hey, the input is length 2, and the output is a scalar. And I want to tell it, now that we've made this chain called LRnet, I want to just produce a little picture of it. So there's a picture. Here's our input, size 2. It goes through this linear layer, which you can just think of as a function, and out pops an output. Okay, so what we want to do is we want to train the network. That is, right now this network is stupid. If I give it numbers and I tell it to make a prediction, it really isn't going to be able to do very well. So to do this, I need to get the data in the right form. And let me just show you what the right form is. You'll see we have our covariates, our features, our independent variables on the left side of the arrow, and what we're trying to predict is on the right side of the arrow. It's just that Wolfram Language's machine learning capabilities, which were made after the statistical capabilities, use a slightly different data format than the statistical capabilities, and so you have to write a little bit of code to transform between the two. My dream is that one day this will not be necessary. All right, but there's our data, and now I'm simply going to tell it train. And what we mean by training is essentially to use the data as a way of modifying the internals of some of the layers. Here there's only one layer, and that layer does need to be modified. We'll go into much more detail on how this all works, but for now you should just realize that that's the concept of training, and the function structure is we give it the network architecture here. We give it the data we're going to be used to train it. I'm going to tell it, hey, train fast. Learning rate means how fast do you learn. This is a very fast learning rate, and for simple problems like this, it's fine. If you use a very fast learning rate with more complicated problems, you can sort of overlearn and make mistakes. And all just means I want you to produce all the output that you can as a result. So this is not going to take long, but just watch it. Here we go. We're about to train our first neural network. And you can see the error getting lower and lower. That's the loss. It's running through the data. You can see basically we've bottomed out. We did as well as we could, and we're done. All right, so now the trained network, which is called trained, you can extract information from it. And among the information I'd like to extract are the coefficients inside the trained network. This is just a way of sort of getting the data out in a form where it's easier to understand for humans. And there we go. We have weights of negative 10.52 and negative 2.85 and a bias of 36.3725. Now let's rerun let's do this just as a good old linear model fit. So I've got linear model fit, prime price 2, and I had crime and access were my basis functions, and crime and access were also, if I spelled it correctly, my variables. And we do it, and look at this. Negative 2.85 times access, negative 10.52 times crime, and our intercept term, which is the same thing as a bias, is 36.3725. And so it turns out that essentially the neural net is implementing a penalty function method, and the penalty that has been selected is the one that is the same, that gives you the same result as the maximum likelihood estimate. So I just wanted to show you that there are similarities between the machine learning and neural network capabilities that we'll see later in this course and what we're seeing here in basic statistics. Just two other footnotes. Some of you may be wondering about R squared and ANOVA. Don't worry, I haven't forgotten about them. Some of you may have been concerned about influence. Don't worry, I haven't forgotten about that either, but I am confident you will agree with me that this video has gone on long enough. So what I've tried to show you here is how to do some simple forms of regression, linear regression, and logistic regression, and most importantly, to understand the concepts behind them. Thank you very much.